Yesterday, we did talk about the different kinds of variables that we can measure, but I want to start off today just by running through those again. So remember, when you are collecting data, you arrange the data in what we call a data matrix. And that means every row represents an observational unit. That could be a person, each row is a different person in your sample. Maybe you're sampling something other than people, like maybe you're working in a wildlife setting and so you're sampling animals. Maybe you're actually working with household units and not with individuals, so you're sampling houses in a neighborhood. Whatever it may be, the rows are those observational units and the columns are our variables, the quantities that we are interested in measuring. So just remember, a variable is a quantity that gets measured. And I will say the word measured here probably has a little bit of a different connotation to what you're used to, because we mean it in a very broad sense. Right? If I ask someone what their favorite color is, I'm taking a measurement because I'm recording what color they tell me. If they say pink, that's the measurement. We do have the classic measurement, like I could ask someone how tall they are, and it's the equivalent of taking, a measuring tape and figuring out their height in inches or their height in centimeters. But anytime you can ask a question or just observe something, we talk about that as measurement. Now, we differentiate between two kinds of variables primarily, numerical versus categorical. And we subdivide those. So numerical is always when we're dealing with numbers. But the numbers can work in different ways. The numbers can be discrete. And if they're discrete, it often means that we're counting or looking at whole numbers. Or it could be anything that occurs with fixed step sizes. So one example could be shoe size. Shoe size happens in half-step increments, 7, 7.5, 8, 8.5. Something else could be the number of siblings that you have. It doesn't matter whether you like your siblings or not, that doesn't make them count less. So your siblings, you could have 0 siblings, you could have 1 sibling, you could have 2 siblings. That's something that we're counting or that occurs in whole numbers. So whole numbers or fixed step sizes tells us something is discrete. Something is continuous if we can always improve the accuracy by using a more accurate measuring instrument. And just think of something we can measure to 2 decimal points versus if you get a very accurate scale, you can suddenly measure it to 10 decimals. Or if you're working in a high-tech physics lab, then you can measure it to 1,000 decimals. So it's just about how accurate does your instrumentation allow you to be. On the categorical side, we said there were nominal and ordinal. Nominal would just be unordered categories. For example, what is your favorite snack? So options could be popcorn, potato chips, tortilla chips, chocolate. You know, you just have categories, but they don't have a natural way of ordering them. Versus if something is ordinal, then you have categories that can be arranged either in ascending or descending order.
I have a quick clarifying question.
Yeah, please ask.
For the favorite snack, what if it was greatest to least, favorite? Could you do it ordinal then? Since it's kind of
Yes.
in order, I guess.
Yes. So the moment you introduce order in some way, it is no longer nominal.
Okay.
Right. But and so there would have to be something that tells you order is being introduced. So
Okay.
so you would tell people rank your snacks from least favorite to most favorite.
Okay. So more specificity should be included.
Yes. Yeah. And there will be something that tells you at that point that order is being added to the question.
Okay. Thank you.
Yeah. No, that's a good question. Yeah. So some things that at face value may seem nominal, the moment you start asking people to order them, then it can become an ordinal measurement. But the typical ones we'll see are already just categories that themselves have a natural ordering. So an example here might be someone might ask, what year of study are you at TCU? And you could say, I'm a first year, or I'm a sophomore, or I'm a junior, or a senior, right? Those are categories, but there's a natural ordering. We all understand intuitively in what way we would line them up, either from first year to senior, or we might start senior and going down to first year. And we could even add graduate student to this because that works with the natural ordering as well. So I'm going to skip over the examples we looked at yesterday and pick up with some examples that we didn't quite get to. So say in a survey, we ask the question, we ask someone what their education level is. And the options are some high school, a high school diploma, an undergraduate degree, a graduate degree. So again, there are no numbers present here, so it can't be the numerical options, but there is a natural ordering, right? Because we can line them up to have an increased level of education. So it would be categorical, but in an ordinal sense, not in a nominal sense. So what I am going to do next is put you into just randomly assigned groups for a couple of minutes. So what we looked at the start of the section is just identifying what kinds of variables we have. But in general, we're not interested in looking at variables in isolation. Variables occur together and affect one another. So the description we give to this in a statistical sense is we want to identify whether there's a relationship or an association between different variables. And here are just two examples. Let's say we have an economist, and this economist, she's studying the financial characteristics of counties in Texas. And she wants to establish what the connection is between average household income and in a county and the percentage of families that own a home in each county. So, it seems reasonable that counties with a higher average income will also have higher percentage of home ownership, right? Being able to buy a home is a function of income. And so the higher the income, the more people you would expect to see who own homes. But here are two variables: household income, percentage of home ownership in each county. Also worth noting, here's an example where the counties, these are our observational units. Right, these would be the rows in our data matrix. And then the columns would be one column for household income, one column for percentage of home ownership. So, we might have, for example, Tarrant County, average household income is maybe 42,500, and percentage of home ownership is maybe 23.5%. And then we might have, that got messed up. Then we might have, Dallas County. Dallas County might have a slightly higher income, 45,800, and might have 24.2% home ownership. Then someone looks at, Travis County. Well, Travis County, maybe the average household income there is 50,100, but only 18.1% of families in the county own a home. But so the relationship, doesn't have to be perfect. It doesn't mean higher income always leads to more home ownership, but there could be a correlation between them. Another example, dietitian is studying nutritional profiles of families in the DFW metro area. This nutritionist, he might want to explore whether there's a connection between how often families consume leafy green vegetables and what percentage of household members have chronic health problems. So, here we might have family one, they eat leafy greens 3 times a week. 5% of people in the household have chronic health problems. We look at family two, they eat leafy greens 7 times a week. Nobody in the household has chronic health problems. Family three, they eat leafy green vegetables 5 times a week. 2% of people in that household have chronic health problems. Whatever it may be, you would here in general expect, we know consumption of leafy greens leads to better health. So here you would expect the more leafy greens consumed, the less chronic health problems you might see. But these two examples, one of them we would expect a very strong relationship, between income and home ownership. Those are closely related concepts. Whereas looking at diet, leafy greens is just one very small component of what impacts health overall. So there might be a relationship, but it might be a very weak relationship. At the end of the day, though, to establish whether there's a relationship relies on collecting good data. So you need to make sure that you measure quantities as accurately as possible, that you collect all the relevant information. And then in addition to that, the data can only help you establish whether there is a relationship. It cannot tell you anything about causality. And causality just means you make a statement that one variable causes another variable. So we might be able to say, we observe a relationship between household income and home ownership. But the data alone can't tell us whether it's a causal relationship. So can we say higher income causes people to own homes? No, it's conceivably possible, right? But the data doesn't actually give us that level of information. The data can only tell us, in general, counties with higher household incomes have a higher percentage of home ownership. So be careful how you write these conclusions in general. So when we're looking at two variables, we want to talk about the presence or the absence of a relationship. We have to be careful. We just said we can't use causal relationship just based on the data. We can't say variable X causes variable Y, not just from collected data. But we can say that two variables are associated with one another or that they are dependent variables. So when we see any kind of connection between two variables, we say they are associated or we say they are dependent. Those are synonyms here. You can use associated and dependent interchangeably to describe situations where a relationship exists, where we'll look at pictures in a minute to describe better what these relationships might be. And then if there is no association, then we say variables are independent of one another. So a pair of variables can only be one of these two things. They can either be related in some way, and therefore we call them associated variables, or they are not related in any way, and we call them independent variables. No pair of variables can be both associated and independent at the same time, because those are opposite concepts. So the way that we start looking for relationships is we have to find a good way to visualize our data, right? Especially if you are collecting two numeric variables. Then the way we can visualize them is using something called a scatter plot. So let's go back to our example where we looked at counties in Texas. And for each county, you collected two numbers. You found the average household income in the county, and then you found the percentage of homeowners in the county. And so we can write down data values, right? We can say 42,000 average household income, 15% home ownership. 48,000 average income, 20% home ownership. 36,500 average income, 18% home ownership. So we can then go and visualize those on what you may have heard called in a math class before a Cartesian plane, where we have an x-axis and a y-axis. So in this case, I'm putting my first variable on the x-axis, average household income. I'm putting my second variable, percentage homeowner, on the y-axis. And I make sure I properly demarcate my axes. In this case, it maybe makes sense to do 5% increments on the y-axis for the percents. On the x-axis, I may do values in tens of thousands. So 10,000, 20,000, 30,000, 40,000, 50,000. Then I can take any data point. The X value here is 42,000. So imagine a vertical line running through the X-axis there. The percentage homeowners is 15%. So imagine a horizontal line running there. And where the two intersect, there I can go and make a dot that represents that data point. So if I read back down to the X-axis, I know what the average household income is. If I read across to the y-axis, I know what percent are homeowners. And so every observed pair, I can go and represent in the same way. Here's the next one, and then I had one that was 36,500 and 18%. There's that one. And in general, you would just plot all of the points, and you might see here, oh, it looks like those points have a slight upward sloping trend. And that's one example of what a relationship or an association can look like. But we wouldn't have been able to see that just from the data points. We had to go and visualize them in an appropriate way to see that. So if you start looking at relationships like this, you will want to start describing them as strong relationships or weak relationships, or strong or weak associations. So in general, if you draw a scatter plot and you have your cloud of points, and you kind of add an outline to that cloud. Here's one example where on the left, we have a narrow cloud or a narrow band of points. And on the right-hand side, we have a wide cloud or a band of points. If the cloud is narrow, that tells us that there is a strong association. If that cloud is wide, that tells us that there is a weak association. Because where does that come from? If we visualize again appropriately sloped lines running through the clouds, then on the left side with the narrow cloud, all the points are close to the line. In the wide cloud, a lot of the points are far away from the trend line. So closeness to the trend line also tells us whether the relationship is weak or strong. And then in addition to looking at weak versus strong relationships, we can also describe linear versus nonlinear relationships. So here's another example of a linear. If you have your cloud of points and you just do a standard ellipse around it, like if it looks like an elliptical shape fits around it nicely, and you can imagine a straight line running through it, that tells you it's a linear association. And the direction of the slope line tells you whether it's positive or negative. If the slope line is trending downwards, it's a negative relationship. Here, if the trend line is sloping upwards, it's a positive relationship. Now, here's another example where, say we just have this kind of looks like a random scatter, right? There's no way to draw a good ellipse around this. It almost looks like a circle might be a slightly better shape, or a box or something. But there's no trend, no upward slope, no downward slope. This would be an example where we would call the variables independent of one another because we don't see any trend. Then we could have a situation where maybe the points are clustered closely to some trend line, but if you start looking at how that trend line behaves, if I track the typical trend here, right, that's not a straight line. So that would be an example of a nonlinear association. The points all follow some trend line closely, but that trend line is not linear. So we're not going to try and describe trend lines in much greater detail than linear versus nonlinear, but you should look at being able to identify those by seeing patterns emerge that are nonlinear in nature. And here's another example of a nonlinear one, where it goes up and then down and then up again. So there's another nonlinear association. And in both of these cases, bottom left and bottom right, those are fairly strong associations because the points cluster close to that trend line. So even when it's nonlinear, you can still have a strong trend. Just make sure if you get asked to classify association, look at whether it's linear or nonlinear, or maybe independent, if it's just a random scatter of points and you see no relationship emerging. And then look at whether the points closely track that trend line or whether they're pretty dispersed around the trend line. That's how we would classify it as a weak versus a strong association. So let's look at an example here. X-axis, or our horizontal axis, shows us for students how many hours they study per week. The y-axis shows us their GPA. So try and draw a cloud around the points, and you'll see there's maybe a bit of an upward sloping line here. But those points are pretty dispersed around the line. So there is some suggestion of a positive, because it's upward sloping, linear association, but it looks fairly weak. Now, it is important, let's just stick with this example. It is important to look at your data and ask yourself if the observations all make sense. So scan the axes and ask yourself if every observation makes sense. So study hours, for example, does it make sense to have people studying close to 0 hours and people studying close to 70 hours? Both of those are plausible values, right? 70 hours is a bit on the extreme side, but not many people are studying or saying they study that much. And then look at GPA. Oh, here we run into a problem. Here's a value that's 4.3. GPAs stop at 4. So here, what sometimes happens is people make recording mistakes in the data. Remember, our data is still dependent on humans entering it into an Excel spreadsheet, for example. So sometimes people make a mistake. So this is a potential data entry error. And so one thing that would be reasonable here is to remove the implausible data point before interpreting the relationship. Because what sometimes happens as well as having a data point that's kind of off the scale like this is it actually messes up just what we're able to see in the picture. You wouldn't think having one off-center point does that much, but it can. It can really mess up even just the proper visualization of the data. So you'd remove that point from your data file, redraw the picture, and then try and interpret the relationship. So be on the lookout for things like that. Let's look at this next example. Here we have a scatter plot looking at data collected from a sample of possums. X-axis tells us the head length of each possum in millimeters. The y-axis tells us the skull width in millimeters. And we want to comment on whether there is a relationship or not. So in general, again here, just looking at the data, you should see there seems to be an upward sloping trend a little bit. So if we're describing what kind of association there is, it's not no relationship because we can see the trend. They're not negatively associated because that would be a downward trend line. Positive makes sense because it's an upward trend line. And just looking at these interpretations, be careful of the word causes. Like from data alone, we cannot make causal statements. So the correct interpretation here is to say head length and skull width are positively associated with one another because we see an upward sloping trend line. So let's just spend a few more minutes talking about causality. Sometimes based on intuition or other information that we've collected, we might suspect that two variables are causally related to one another. If that is the case, we call them by special names. We would call the first variable the explanatory variable, and the second variable the response variable. So the explanatory variable is the one that might affect the response variable. So just remember, these are labels that we apply. It still doesn't mean that there's a causal relationship. We are just conveying with the language that we suspect there may be a causal relationship and which way around it works, right? If we look at our example of how often do you eat leafy green vegetables, how many times did you go and see the doctor last year? Well, consumption of leafy green vegetables may have an impact on health, but it's unlikely that seeing your doctor has an impact on how often you eat leafy green vegetables. So you can very often figure out if there is a causal relationship, which variable is the explanatory variable, which one is the response variable. And in other cases, there's just no hypothesized relationship. And so if there's no hypothesized relationship, do not apply labels in such cases. Then we've talked a lot about data collection now and identifying relationships, but we also have to ask ourselves what the study looks like in a larger context. And there are two types of studies that we will see in this class: observational studies and randomized experiments. And we often drop the word randomized, we just call them experiments. So in an observational study, these are characterized by situation where we only are recording the information available to us. Specifically, the people conducting the study do not actively intervene in the study. So they don't try to affect the behavior. For example, we observe whether someone smokes, and how often they have bad allergies. An intervention would be telling them to stop smoking, or an intervention would be giving them a new allergy medication to try. But if it's observational, we only observe. Like, you take a sample of people and you just observe and record the information. Do you smoke? Yes or no? How much do you smoke? Oh, 5 cigarettes a day, 20 cigarettes a day, whatever it may be. And then we ask them, you know, how many times in the last 3 months have you had bad allergies? So the information already exists, and we are just recording that information. We are only observing what is there, observational study. The other kind of study is a randomized experiment, and this is defined by active intervention. And active intervention could take a lot of different forms. It could be giving participants a new medication to try. It could be asking people struggling with anxiety to start meditating. So here, whoever is running the study, they often want to show that they have a way of solving a problem. They have a way of helping with a disease. They have a way of reducing anxiety. They have a way of improving healthy eating habits. And so they actively, after taking the sample, they actively intervene in some way by giving people a medication, by having them take a class, by sending them to a seminar. A lot of different possibilities, but there's active intervention. And so that is what defines it as a randomized experiment. How does this relate to causation? Well, we've said already, just because two variables are associated does not mean that they have a causal relationship. But we can, from experiments, if we do an experiment, we can typically infer causation from that because we know how the intervention is being done. So in observational studies, all we can say in observational studies is that the variables are associated. In a random experiment we can make causal statements. So we're going to delve a little bit deeper into the idea of observational studies, and we're also going to talk about how to take good samples and what kind of samples are available to us to take. So whenever you start off on a research project, it is important to make sure that you clearly sit down and define the research question. So as a statistician, I've been in a situation a couple of times where people threw together a questionnaire. They knew they had to collect some information, so they put together a questionnaire, sent it out to the group of interest. People sent back their replies. They bring me the data to analyze, and are then disappointed when I tell them that they didn't ask the questions that answer, the survey didn't include the questions that answer their actual research question. So it's important to start off with a clearly formulated research question. And to do that, you also want to identify who the population of interest is. So we talk about a target population as being all individuals, or remember, sometimes we don't work with people. So in a general sense, all objects relevant to the research question. So you want to make sure you properly identify everyone who that research question is relevant to. If you're measuring something about, health, are you just looking at the health of people in Texas? Are you looking at the health of women who have given birth in the last year? Are you looking at the health of children under the age of 12? Make sure you understand who the target population is. Then plan how you're going to collect your data, because you want to make sure that all members of your target population have the possibility of being represented once you've collected your data. So we talk about this as sampling. And a sample, our definition of that is a sample is a subset of the target population. And a subset means a group that is part of. So I know we all have some intuitive idea around who a sample is, but now we have to make sure that we view the sample in the context of the larger target population, right? We have this larger group that we're interested in studying. Because we can't go and measure diet and exercise information for every single person in Texas, we take a subset. We get a hopefully representative group from the larger population and we study them. And let's look at an example here. This is a study that was published, a few years ago already. New York Times did a write-up of it in 2012. And the study looked at whether people can become better runners simply through the act of running. So does running on a regular basis result in you becoming a better runner? Now, this was a study done by a group at the University of Exeter, which is a university in England, and it was published in a well-regarded medicine and sport journal. And the general question they were trying to answer is, can people become better, more efficient runners simply by running? So here, without intending to maybe, but they defined who their target population is. They wanted to look at all people, right? If we just look at all people who might be runners or who might start running, can they improve their running ability simply by running? So this defines the target population. Well, the study then went and looked at a group of adult women who'd recently joined a running group. All of these women agreed to be studied. They were healthy, they were in their 20s or 30s, they were of typical weight and completely new to the sport of running. So it's a valid sample in the sense that these women participating in the study, they do form part of the larger group of all people. But the study kind of missed the boat on this one, because if they really wanted to make a statement about all people, then they shouldn't just be studying women in their 20s and 30s, right? That's a much narrower focus than what the intent of the original study was. So in this case, as we said, the population of interest was all people, but the sample looked at women in their 20s and 30s who are healthy. So the sample is in no way representative of the population of interest or the target population. So in this case, when we talk about the generalizability of the study, the results do not extend beyond women in their 20s and 30s who are healthy. So having a sample that's not fully representative of your target population can be okay. You just need to understand the limitations then. Whatever your conclusions are, they're not going to apply to everyone. They can only, or at most, can be generalized to groups of people who are similar to those people in your study. So this is an example where you have to very carefully sit down and define your target population so that you know the sample that you collect is representative of the target population. The other thing we have to be careful of is dealing with anecdotal evidence. So we talked in the previous section a little bit about observational studies versus experiments. And we said in experiments, we can often make causal statements. If you do an experiment and you actively intervene in the study process, it can create a situation where you can make a causal statement. If you don't, if you're only observing data, you are only able to talk about associations or relationships existing. How does that apply in a more broad setting? Well, if we look at smoking, anti-smoking research has been around since the 30s or 40s. At the time, cigarettes were very popular. Like you couldn't go and watch a movie in the 30s without half the people in the movie smoking. Like there was a big push for making smoking very socially acceptable. then, in light of people trying to do the smoking research, there was big pushback. People would make statements such as, oh, I have a family member who smokes 5 packs of cigarettes a day, and he is in perfect health. Well, this is an example of anecdotal evidence, right? It's not collected through any scientific process. It's a single observation. Or anecdote is a story, right? It's just one person making a statement about what they believe to be true. So it comes from a very limited sample size, usually a sample size of 1, and might not be representative of the larger population. So with this example of smoking, over the long run, we have now collected enough information to say that there seems to be a strong association between smoking and certain types of cancer, for example, lung cancer. But we are still in a situation where we can't necessarily make causal statements. Right now, we've gotten to a point where most people believe and trust that smoking can cause cancer. The only way to really make a causal statement is to run an experiment. But this experiment would then involve taking people, forcing some of them to smoke, even if they don't want to, because we need to actively intervene. We need to tell some people to smoke. We need to tell other people to not smoke in order to make a causal relationship. To study whether people get cancer, like you can hopefully hear that this would be a highly unethical experiment. So there are certain times where we will never fully get to a causal statement because we can never go and run this experiment because it would be highly unethical. In those cases, we just rely on associations, and we know there is a strong link. We just can't make a causal statement. Now, when you do look at anecdotal evidence, that means you're looking at information that represents 1, maybe 2 people or 2 different observational units. And when the sample size is that small, you're just not dealing with the situation that represents the broader population. Also, anecdotal evidence is often information collected in a haphazard way. I know a person who. That's a great way to start a sentence if it's haphazard information collection, right? My uncle does this, or I have a brother who. There was no scientific thought given to collecting different units from the population. You just kind of know people. That haphazard type of data collection, again, might be a situation where it only represents the most extraordinary or atypical cases. Someone who smoked 50 packs of cigarettes a day and never had any adverse health problems. Now, anecdotal evidence is the one extreme where you have like really small samples and not collected in a good way. The other extreme is doing a census. So when we do a census, rather than trying to sample, we collect information from the entire population. And you should have some familiarity with the census because we had one happen last year. But every household in the country had to be counted in the census. And so here, you're dealing with something that's very time consuming, very costly, because you're trying to get information from every person or every object in the entire population. There are a lot of challenges to doing a census. And really, I would say the only reason it still happens every 10 years in the US is because it's mandated by the Constitution. The Constitution tells the government to go out and do their best at counting every person in the country. But in doing so, the census runs over say, a 6-month window. Over that 6 months, the population is constantly changing. New people are being born, people are dying. So who exists at the start of the 6 months is not the same as who exists at the end of the 6 months. You know, maybe you could argue, well, there's not that big a change in a population over 6 months. But definitely you are not doing a perfect count. So there are a lot of challenges with census. And very often, if you just do a well-designed study involving sampling, you can get better information than trying to wade through a census with all the thorny issues that come with that. Taking a census can be way, way, way more complicated than trying to take a sample. In fact, this is something we saw in the news last year with the census as well, but here's a story from 10 years ago talking about how undocumented immigrants were very reluctant to fill out the census. And we know that was happening last year as well. Side note that probably no one is interested in, I was in Arizona last week, and so I happen to know that KGZZ is the call sign for the Phoenix. Well, I guess it's in the story. It's the NPR affiliate broadcasting out of Phoenix. Okay, so when we want to therefore collect good information from a target population, sampling is the most natural way to think about that. So what you then want to ensure with sampling is that you do it in a way that you get representative people or representative objects from the population. Think about it like cooking, right? You might cook a pot of soup, and maybe you have 3 different kinds of vegetables in there. And if you take out a ladle of soup, there's a chance that not all the vegetables are occurring in that ladle. Like if you have chunks of bean and chunks of potato and carrot. You know, it's possible to take a ladle of soup and not have any carrot in it. But more often than not, the ladle will have all the vegetables in it. So sampling, just by virtue of the randomness, ensures that most people or most objects have a good chance of being representative in your sample. We then talk about 2 kinds of questions that we try and answer. We can sometimes just do an exploratory analysis, which is just basic description of the sample. We talked some about summary statistics yesterday. This is where you just calculate summary statistics to understand what percentage of people have high school diplomas, what percentage of people are homeowners, what percentage of people regularly exercise, right? Summary measures, exploratory analysis. If we are trying to make a statement about the larger population, that gets into inference, and that's something we'll talk a lot about in the second half of June term. But either way, the most important thing is that the sample you take should be representative of the entire population. If you have this pot of soup and you didn't stir it well, and it's been sitting on the stove and all the vegetables are at the bottom, and you just scoop from the top, you might not think that there are any chunks of vegetable in the soup. So that's just kind of an analogy getting at making sure you sample from the entire population and not just skimming a teaspoon of soup off the top of the pot, rather than digging down with the ladle and getting some of the heavier vegetables at the bottom too. So you want to sample in a way that is equivalent to like stirring the pot of soup and then scooping out, so you get something that is representative of the entire situation.